All right, cool. So group one, how many N's are in the first chemical formula there? Blow that up a little bit. Yeah, there we go. How many N's? Group one? Two. Yeah, there's no number after the nitrogen, so that means there's one, but because I have two of that group, distribute that, we get two. Group two, how many H's? There's 8. 4 in an ammonium ion. 2 ammonium ions gives me 8. How many sulfurs? Group 3? 4. Are you sure about that? No. No number after S? Right, there's no number after S? So it's understood to be...
I give up.
Okay. Somebody else? S? Nick, how many O's are in H2O?
2.
How many O's?
2. One of those things.
How many H's are there?
1. 2.
There's 2 of them, right? That number tells you how many H's you have. How many O's are there?
1.
There's 1. There's no number, so it's understood to be a 1. Take one last shot at S. How many S's?
1.
There's 1. There we go. 15th time is the charm. What about oxygen? Group 4.
4.
There'd be 4. Show our hands, we got that. 2, 8, 1, 4. All right, looking good. Any questions I can answer? This is the first step to doing a molar mass problem, to balancing an equation, to doing percent composition, to doing an empirical formula. You have to have them. All right, so that's group 4. Group 5, how many barium atoms?
1.
Yep. How many nitrogens? Group 6.
1.
Yep, there's 1 nitrogen in nitrate. How many nitrates do you have?
2.
2. So distribute that. How many N's do you get?
6.
2 times 1?
Or 2 times 2.
2.
Sorry,
Everyone good with that? 1 nitrogen per nitrate. 2 nitrate groups would be 2 N's. How many O's would there be? Group 7.
6.
6, yeah. 3 oxygens per nitrate. 2 nitrates would be 6. Show our hands, we got that? All right, good, good, good. Any questions I can answer? All right, group 1, how many hydrogens?
2.
Yeah, there's 2 hydrogens per molecule, but because we have 3 molecules of hydrogen, you'd have to distribute that. That would be 6. Everyone good to go on that? 3 times 2 is 6. All right, how many strontiums? Group 2.
9.
There would be 9. 3 strontiums per formula, but then because we have 3 formulas, 3 times 3 would be 9. Good. How many phosphorus atoms? Group 3.
2.
Right, so phosphate has 1 P. This would have 2 phosphates, so that would be 2, but that's how many P's there are in one formula, but I have 3 of the formulas. So triple that, that would be 6. Everyone comfortable with that? So I like to pretty much just ignore the 3 at the very beginning, whatever the coefficient is. I'd say, well, there's 3 strontiums, there's 2 phosphorus, and there's 8 oxygen. And then I would simply go back and triple everything. That kind of saves you from making some mental math errors when like doubly distributing. All right, I think we're back up to group 4. How many oxygen atoms?
24.
Yeah, so 4 times 2 would be 8 times the 3 molecules or 3 formulas would be 24. Good. Any questions on that? Quick show of those 4. How many did you get right? Good, good, good. Do you know why this would also be 4? IV. There you go. 1 before 5 is 4. Roman numerals. Good. All right, let's go ahead and take a look at balancing chemical equations. Even though we're not quite ready to balance them, we can still count atoms on both sides of the equation. So where did I leave off? Group 3, I think. Maybe, let's go, oh, group 5? Okay, group 5, how many NAs on the left? 1. Group 6, how many NAs on the right?
1.
1. Group 7, how many CLs on the left?
1,
1. How many CLs on the right? Group 1.
2,
2. How many Fs on the left? Group 2.
2.
And how many Fs on the right? Group 3. 1. So at this point, that's all you have to do, but you'll notice that that equation is not balanced. We don't have the same number of atoms on both sides. So eventually what I'll teach you to do is to go back and add some not subscripts. We can't change any of those chemical formulas, but you could change how many of them you have. So I need some more CLs. Well, you could simply put a 2 there. That changes the Na to a 2. That changes the Cl to a 2. Well, now I need 2 NAs and 2 Fs on the right, so you'd go back, put a 2 there, changes Na to a 2, changes F to a 2. So again, we didn't need to do that for the homework, but that's exactly how I'm going to teach you to balance those equations 2 units from now. Anybody remember what type of reaction this is? This is what you did in the halogen reactivity of elements lab. You have a single element potentially swapping places with another element. The one element that's single is kind of replacing the other element. Single replacement. Again, we'll do that in about 2 units when we go over the different types of reactions. All right, let's go ahead and take a look at this bottom one here. Group 7, how many NAs on the left? Group 7?
3,
3. Group 1, how many NAs on the right?
3,
3. Group 2, how many BRs on the left? Per formula, but we have how many formulas? Yeah, so you're going to have to distribute that 3. There's 3 BRs on the left. Group 4, how many BRs on the right?
2.
2. Group 4, how many H's on the left?
3.
3. Group 5, how many H's on the right?
2.
2. Group 6, how many P's on the left?
4.
That's how many O's there are. What number do you see after P? Just 1. Group 7, maybe? How many P's on the right?
1,
1. Group 1, how many O's on the left?
4,
4. And group 2, how many O's on the right? 4. Now sometimes what you'll see us do, especially to make it a little bit easier with balancing equations, you'll notice this phosphate group is always the phosphate group up here. So rather than splitting apart the P's and O's, sometimes what we'll do is we'll just leave that all together and we'll say PO4. How many PO4 groups did I have here? Well, I had one of those groups. How many PO4 groups there? I had one of those groups. So sometimes we leave those polyatomic ions together. You'll notice that the only thing that is causing this equation not to be balanced would be the H's and the BR's. I don't want 2 of them, I want 3 of them, so eventually we'll just go like that, put a 3 there, cross it out, 3, 3, and we're done. So then that's how we'll balance those equations. Any questions on that? Alright, so if you take a look at our essential questions for today, we actually have 2 of them. So the one that we just wrapped up would be, how do you calculate an atom inventory? In other words, the number of each type of atom in a formula. And then today we're moving on to this question. How do you calculate the formula molar mass of a compound? And the second part of the question is, how do you name and write formulas for hydrates? A hydrate is a special type of compound. It's going to change how we calculate the mass of it. It'll change how we name it and write formulas. So we're actually going to tackle those 2 questions today. So before we move on, quick conversation in your small group. How do you calculate an atom inventory? How do you figure out how many of each atom there is in a formula or in a chemical equation? Quick conversation in your small group. Yeah, go ahead. All right, sounds like we're wrapping that conversation up. So, number 9, Sawyer, how do you calculate an atom inventory?
If there's an exponent that can be distributed, you distribute it, and then after that, you just count on them.
Okay, so by exponent you meant a little number that goes below, like a submarine, so subscript? Yeah, so you'll distribute subscripts inside parentheses. What if there's a big coefficient in front of a molecule telling you how many molecules you have? Lily, what do you do with that? Yeah, you'll multiply every atom in that formula by whatever the coefficient is. If it's a 4, you'll quadruple everything. Good. Any questions on that? All right, so let's go ahead and take a look at slide 34. If we're going to talk about molar mass today, we should probably just stop and review and make sure we understand what a mole is. I know it's been a little while since we had mole day, but the mole is a counting unit. Just like a dozen represents what number? 12. A couple represents what number? 2. A mole represents 6.022 times 10 to the 23rd. It is a molecular counting unit. Because molecules are so small, we lump them into a really huge number, and we say we have 1 molecular unit of it, which is 1 mole. How big is it? Well, a trillion is big enough, but this is 602 billion of those trillions. It's a huge number. You might be wondering, well, how did we determine that it was that number? Well, a long time ago, we didn't really know what the mass of the elements were yet, but we knew how the masses were related to each other. So when we broke apart different compounds, let's say methane, we knew that carbon weighed 12 times as much as hydrogen. And we knew that oxygen weighed 16 times as much as hydrogen. So when we came with those, and when we determined those ratios, we said, well, let's kind of pick a middle element like carbon. We know it weighs 12 times as much as hydrogen. So let's just say we have 12 grams of hydrogen. The question is, how many particles would be in there? When we work backwards, we figure out that you'd have pretty close to a mole, 6.022 times 10 to the 23rd. It's named after Avogadro, not avocado, even though you can make guacamole out of it. But it's Avogadro. He came up with the idea of certain size gases always have the same number of particles. Nobody really believed him, so when they actually determined that there was this number, 6 times 10 to the 23rd, they named it after him. Any questions on that? Question?
Is this one supposed to be the
Yeah, it got pushed down today.
Oh, okay.
Yep.
Thank you.
All right, so what about atomic or formula mass? We can't really say it's the same thing because an atom on the periodic table would just be one atom. But if we have certain formulas put together of those atoms, that would be a formula mass. So the mass of one atom would be atomic mass. The mass of one formula, whether it's H2O or BeCl2, that would be formula mass. So the mass of one atom on the periodic table, because it's so small, we can't weigh it in grams. So that's why we're going to use the atomic mass unit, or AMU. The cool thing is we determined what we defined what an atomic mass unit was based on the molar masses. So if carbon weighs 12 grams per mole, we simply divided that by Avogadro's number, came up with a really small unit, and we said, well, that unit will be the atomic mass unit. So when we have 12 of those, well, that's one atom of carbon. So we pretty smartly defined what an atomic mass unit was so that the atomic mass and the molar mass is going to be the same. If you take a look at copper on the periodic table, copper is element 29. You can see the periodic table over on the side has way more units than what we normally use in class, but the class periodic table will always have 2 decimal places. That should be good enough for most of our calculations. So that's the mass of an atom. How do you figure out the mass of a formula? You'll simply add up which atoms you have, multiply by their masses on the periodic table, and then you'll add everything together. So a good example would be water, H2O. There's 2 H's, each one of them weighing about 1 atomic mass unit, so that would be 2 atomic mass units. Oxygen weighs 16 atomic mass units. You put 2 and 16 together, you get about 18.02 atomic mass units. So because that's the mass of one formula, We'll call it a formula mass unit or an atomic mass unit. Questions on that? All right, as far as molar mass, it's going to be the same exact calculation because the numbers on the periodic table also represent molar masses. So carbon weighs 12.01 AMUs, but if you have an entire mole of carbon, it's going to weigh 12.01 grams. Same thing with copper. Rather than 63.55 AMUs, it'll be 63.55 grams. Same thing in finding a molar mass of a chemical formula. You'll figure out how many atoms of each element there are. You'll multiply by their masses from the periodic table, put that all together, and you'll get the molar mass of the compound. Questions on that? All right, so let's do an example. We've got the chemical formula, Cu2, CO3, in parentheses, OH subscript 2. So the very first thing we're going to have to do is count each and every one of those atoms. How many copper atoms are there? 2. So Cu equals 2. C, how many carbons are there? 1. You got to be a little careful with the oxygens because I have oxygens here and oxygens here. I have 3 here. How many do I have right here? 2. So I have 3 here, 2 there for a total of 5. Good. And then how many hydrogens? 2. Now, do we know how much copper weighs? Sure. Periodic table would say 63.55. So that's what we're going to do. Go. 63.55. That would be atomic mass units. What about carbon? How much does carbon weigh?
12.01.
Yep, 12.01 atomic mass units. How much does oxygen weigh? 15.9994, we'll call it 16.00. And hydrogen weighs 1.01. All right, so now we basically have to figure out what these masses are. What's 63.55 times 2? 126. 127.10? Someone check my math? 0.10, yep, two decimal places, 12.01? There's only one of them though. What's 5 times 16? 5 times 6 is 30. 50 plus 30, 80. Everyone good there? And finally, 2 times 1.01, 2.02. What do you think I have to do to all these masses if I want the total mass of this formula? Add them all together. So 129, 139, 219, 220, 221, I don't know, 221.13-ish. Somewhere in that ballpark. Add them up, see what you get. 121.13. Now, if I wanted the mass of one formula, you would say atomic mass units. If I had an entire mole, if I had lots and lots and lots of those particles, I would say, well, I have 221.13 grams per mole. So it's the same calculation, it just depends which units you use. Questions on that? All right, last thing we have to do is, because some of our compounds would be hydrates for today, we have to figure out what a hydrate is. So at any point as you're working on calculations, you can always check my answer key, which would be in my teacher slideshow. So feel free to do that as you're working on homework problems tonight. Well, let's talk about what a hydrate is. When you hear the word hydra or hydrate, what comes to mind? Water. So something about these compounds has water in them. The compound on the right up here, which is purple, is a hydrate. Does it look wet? No. Does it look like it's dissolved in water? No, and that's because it's not. A hydrate is simply a compound that has water inside of its solid crystal structure. So again, it is a solid, but it has water inside that network of atoms all lined up. The formula is going to use this dot up here. So I know sometimes in math class we use that to show that we're multiplying something. Try typing option 8 on your keyboard and see if you get a dot. Yep, so that's exactly the symbol we're going to use. It just says, hey, watch out, this compound has water inside of it. It's going to be called a hydrate. A good example would be cobalt 2 chloride dot 6H2O. So again, we're not multiplying by 6 waters, but 6 waters would make this compound heavier. Because if you drink water and are hydrated, you have more stuff inside of you that would make you heavier.
Would it still dissolve into water?
Oh yeah, it could definitely dissolve in the water. Yep. They use this technology in a little sticker in a lot of technology or technological devices to tell whether people are lying. Any ideas? A sticker used to be blue. When that sticker is exposed to water, now it turns purple, and they can tell whether people are lying. Any ideas? This used to be a little bit easier to see, like when a cell phone was a little bit easier to open up, and now with like an iPhone, you have to like get a little special screwdriver, use a suction cup to pull the screen off. You could definitely do it, but in like the older cell phones, you just pop the back off, there was a battery that had a sticker in it.
Doesn't like if they were sweating, just they were like sweating.
Potentially, but that sweating probably won't ruin a cell phone. What will ruin a cell phone though? Dropping it in water. So sometimes people would take their cell phone back to the store and say, I don't know what happened, but my cell phone doesn't work anymore. I think that's your fault. I would like a new cell phone, please. And the first thing the people, the Geek Squad, would do would open it up, and there's a little sticker on the back of the battery. If that cell phone had been dropped in water, whether it was a toilet or somebody dropped it in, I don't know, the swimming pool, or they had it in their pants pocket, or dropped it in the fish pond, if that sticker went from blue to purple, it doesn't matter how much rice you put it in, whether you try to dry it in the sun, that purple sticker is never going to go back to being blue. Because once that cobalt 2 chloride is exposed to water, those little water molecules go into that crystal structure and it's never going to come out. So if that sticker was purple, they knew that you somehow got your cell phone wet and they weren't going to give you a new free phone. All right, so as far as naming the compound, you're simply going to add the word hydrate onto the end, but it has to have a prefix telling you how many water molecules it is. So last unit, or on the cornerstone, you would have named this cobalt Roman numeral 2 chloride. Why? Because cobalt could be a +2, +3, or maybe a +6. I'd have to take a look. But because cobalt chloride is a -1, there's 2 of them. That's a -2. The cobalt would have to be a +2. So that's old news. When you see the 6 H2Os, though, 6 would be hexa, and then you're going to add hydrate, so it's cobalt 2 chloride hexahydrate. So most ionic compound names only have 2 parts. Okay. If it's a hydrate, you'll have a 3rd part that has hexahydrate or whatever prefixes on the back of your periodic table. So if you need some help with those prefixes, they're back here. 1 would be mono, 2 would be di. I know sometimes we use bi, like bisection in geometry class or whatnot, but in chemistry class we use di. 3 would be tri. If you're really into Nintendo, you might have known 4 was Tetra because of which game? Tetris. All the shapes in Tetris were built out of 4 blocks. And when did you get bonus points in Tetris? You got points when you canceled out a line, but you got super bonus points when you canceled out 4 lines at once. So 4 would be Tetra. That's where we get Tetris from. 5, from 5-1, it's usually pretty easy, like a pentagon, a hexagon, a heptagon, although sometimes in geometry class they use a septagon. We'll use hepta, and then after that it's octa, nona, and deca for like a decade. Any questions on prefixes? All right, just to make sure we're good on hydrates, go ahead. Well, here's a picture of what a hydrate looks like. So here's the cobalt ion, here's the 2 chloride ions, but now we also have 6 water molecules. The negative oxygen attracts there, and you put that all together, that would be 1 formula unit of cobalt 2 chloride hexahydrate. So just to make sure that you can write a formula and name the compound, let's try these 2 real quick. Discuss it with your small groups, and then we'll check and make sure we're good to go. While you're working on that, I'm going to pass out the 3D periodic table that my TA Gavin made. This was his prototype, and he made some revisions to it. He made a final draft, and then he's coming up with like a little worksheet that goes with it. So if somebody in here, you can't do electronegativity, but if you wanted to do a different atomic periodic trends property like ionization energy or atomic radius, you could do that. So here's a three-dimensional periodic table. You guys can go ahead and pass those around. Luke, when they get back to you, can you bring them up here? Cool. Sure. Oh, sure. Lily, any questions? Here we go. All right, just to make sure we're on the right track, what are you going to say for FE? Number 5, Ewa. Iron. And when you look at the periodic table, what do you notice about iron? Not that periodic table. That one doesn't have any charges on it. Let me get you this one here.
Has more than
Yeah, it has more than one charge, so we're going to have to leave some room for a Roman numeral. What would the options be?
2, 3, or 6.
Yeah, +2, +3, or +6. We won't figure it out until we do the next part. What are you going to name NO3? Number 20, Nick. NO3 would be called what?
Nitrate.
Yeah, nitrogen ate some oxygen, so nitrate. What charge does nitrate have? Maybe you can pass this back to you. Nitrate on the back of the periodic table would have what charge? It's in the -1 section. Well, yeah, because there's 3 of them, that would be a total of -3 charge. So what charge does the iron have to be? Tobin?
3.
3. And how do I show that it's the iron +3 version?
I.
Captain. Notice how it's not lowercase LLL. It's capital I, capital I, capital I. Even though a lowercase l kind of looks like a capital I depending which font you're using. All right, so it's iron 3 nitrate, and now how do we finish off the third part of the name? Number 4, Luke. Prefix for 7? It's close to hexa. Hexa would be 6. It's close to September because that used to be the 7th month. Yep, hepta. And what do we have to add to that to finish it off? What type of compound is this? Number 9, Sawyer. Iron 3 nitrate hepta water. Hydrates. You want to go out and use the water fountain? It's right out there. Heptahydrate? Nope. Okay. So it would be a 3-part name. Iron 3, nitrate, heptahydrate. Questions on that? Show of hands, we had that. Iron 3, nitrate, heptahydrate. Okay, good. Any questions on that? All right, well, what about the bottom one? You see chromium III. What are you going to write down? Ryan? Symbol?
CR.
Yep. With which charge? Aren't there a couple options?
3.
Yeah, 3 plus. And then nitrate is going to be what symbol? Number 23, Tobin. Yep. Nitrate. Yep, so NO3. That's a minus. How many of the NO3s do you need to cancel a plus 3? 3, just kind of like this one. So Cr, not iron 3 nitrate, but chromium 3 nitrate. And this might be what you tell your grandma to do if she's kind of dehydrated. Non-hydrate. So what are we going to write down for that? Number 2, Ryan. You all set? Sure.
Is this talking about,
How many bromine atoms should your Lewis dot structure have? So the formula is MgBr2. But yeah, you wrote 14. Right, but it doesn't say how many electrons are there or how many bromine atoms should your Lewis dot structure start with. Okay. Ryan, what'd you say for non-hydrate?
I'd like the dot.
Mm-hmm. Option 8.
And then 9.
9. H2O. There you go. That's it. Non-hydrate. Show of hands, we had that. Sweet. Would you agree water would make that compound heavier? So that's one thing I have to keep in mind when I'm making solutions in here. If it tells me to weigh out 1 gram of chromium 3 nitrate, I need 1 gram of chromium 3 nitrate. Whereas if my bottle says chromium 3 nitrate, not a hydrate, I'm going to have to scale that up and take into account the 9 waters, because 1 gram of the non-hydrate isn't going to have 1 gram of chromium nitrate. A lot of that mass would just be water. Questions on that? All right, let's go ahead and take a look at your homework then. So if you are the sort of person that needs maybe just a little extra example problem, we've already done one in your slideshow, but on page 20, that would be like an extra example. So again, you're not doing page 20, but there's actually 2 examples at the top here. So if you need to see 2 more examples of how to count the atoms and then multiply by their masses from the periodic table and add everything up, you could take a look at that. Your homework, though, is going to be what I have labeled as page 21. It should say molar mass or gram formula mass, and you're going to do the even problems. Would you agree all of these answers are on the teacher slideshow? Yes, so can I just accept for homework credit just final answers? Just typing things into the calculator, writing down the total mass? No, that's not going to get you any credit, unless you come in tomorrow with like a Nobel Prize hanging around your neck. So if you have a Nobel Prize, great, then you probably wouldn't have to show the work for this. We obviously don't have Nobel Prizes in chemistry, so you're going to show the work, final answer, and then you can check and see if you got it right. Any questions? All right, rest of the time is yours. 7 even problems on page 21. Once Joey gets done.
so just put
Yep,
it
you're all set.
together.
Great, thanks.
Thank you. And then I can show you the whole